Hi folks, and welcome back to Math with Captain Rod. I'm making this video here to help people understand how to set up integrals for arc length calculations. So what we're going to do here is we're going to take a look at the function y equals x squared. I always like to use a nice easy function when I'm starting out new topics with people. I've drawn a quick sketch of it, what it looks like in the first quadrant, and what we're going to do is we are going to try to set up an integral to calculate the length of the arc along this curve. So from x equals 1 to x equals 4. So the first step in any sort of either length calculation or area calculation or volume calculation in math is to break the problem up into little what are called differential elements. So I'm going to do that now. Because we're trying to calculate an arc length, what I'm going to do is break this curve up into little pieces. That little piece has a very, very small length. Now, how small that length is depends on your intent on how you're going to solve it. Now, I'm going to be setting up an integral to solve this. So I'm going to say that this has a length equal to ds. We're going to make that a differential element. So we're going to be imagining this infinitely small. Now, it's important to realize that's not a dx or a dy. Dx would be a differential parallel to the x-axis. Dy would be parallel to the y-axis. Make sure I said that right. Dx would be parallel to the x-axis, and a dy would be parallel to the y-axis. This is neither of those. This is a little infinitely small arc length. Now, if I kind of take this and kind of blow it up here, right? Here's my ds. What we can do here is we can break this down into a dx and a dy. We can make this little triangle here. And we can come up with an expression for ds by using Pythagorean theorem, because ds is the hypotenuse of this triangle. So we can say that ds squared is equal to dx squared plus dy squared. Now, ultimately, what we want to do, and I'll write this over on the left, is we want to add up all these little ds's as x runs from 1 to 4. And that's what the integral does. Basically, it's an infinite addition. Now, what we want to do here is solve this for ds, and you would do that by taking the square root of both sides. And the next step is kind of a strange factoring step. There's two things we can do here. We can either factor out a dx or a dy, and which one you do depends on which way you want to set up the integral. Because I'm setting this integral up with respect to x, I'm going to go ahead and factor a dx out of that. Now, inside this radical, when you factor this dx out, you're going to want to do this. Factor dx squared. This is going to become 1 plus dy dx squared. Notice that if I redistribute this, the dx squared times this gives me the dx. The dx squared times this gives me this term. This guy right here is a very important term to understand. This is not d squared y dx squared. That is not a second derivative. That's a first derivative squared. Okay. Now, when we square root that dx, here's what we have. We have that ds is equal to the square root of 1 plus dy dx squared. And by the time we square root that dx, it comes outside the radical. And that's what we're looking at. So this expression, square root of 1 plus dy dx, the quantity squared here, times dx, is an expression that gives the infinitely small length of this green differential element. Now, had we factored a dy out, we would get virtually the same thing, except under here we'd have 1 plus dx dy, the quantity squared. And which one you factor out depends on which way you feel like setting up the integral. Right? So, getting to our integral here, this is going to equal the integral from 1 to 4 times the square root of 1 plus 4x squared dx. Now, the 4x squared is coming from this, right? This term is dy dx, the quantity squared, and I'm looking right here at the function I'm using. Dy dx would be 2x, and then we're squaring that, so that'd be 4x squared, right? So what Again, the purpose of this video is just to talk about how to set up the integral. You start by drawing your differential element. You make this little right triangle here where your ds is going to equal, well, ds squared is going to equal dx squared plus dy squared by Pythagorean theorem. You factor out either a dx or a dy depending on which way you want to set up the integral. And here's the integral all set up here. Now, when you do arc length calculations, or in the next example I'm going to do a surface area calculation, the integrals tend to be pretty tough, and the point of this video was not how to work the integrations. The point of this is how to set them up. Here this arc length integral has been set up, so I'm pretty well going to end the video here. I would point out that these integrals are all done very easily numerically, so anybody watching this, if you're familiar with numerical integration, those are great techniques for these. I've got a video series on how to do these using Microsoft Excel, and there's lots of people out there with similar videos, so I think that numerical is a good approach for any of these arc length or surface area type problems because they tend to give you somewhat difficult integrals. Now this one is not overly difficult. I'm sure that one can be done with probably a trig sub or something like that, but I'm going to go ahead and end that video right there. I hope that this helps with how to set up integrals for arc lengths. Have a great day.